Hello, my name is David Pryor, and I'm joined here by Daniel Monazah. Our group is doing Narrowband IoT LTE waveform generation. The Internet of Things is the concept of connecting people, things, processes, and data. This idea has led to a surge of network-connected devices around the world, with the quantity of IoT devices increasing exponentially. The number of internet-connected devices is expected to reach 50 billion by 2020. To be feasible, these devices must be extremely low power, responsive, and reliable. To accommodate the design requirements of IoT devices, 3GPP has defined a standard that describes a narrowband implementation of LTE. The goal of this new standard is to provide a cost and power efficient protocol for the low-rate communication used by IoT. The goal of this project was to generate, transmit, and decode an NB-IoT downlink signal. To achieve this, the following tools were utilized: MATLAB for signal processing, Atom Pluto for signal transmission, and RTL SDR coupled with SDR Sharp for reception. First, we're going to give an introduction to the concept of narrowband IoT. We'll go over narrowband frame structure, primary sync signal, secondary sync signal, reference signals, physical broadcast channels, physical downlink shared channels, and physical downlink control channels. The following are similarities between NB-IoT LTE and traditional LTE. Both systems utilize 12 subcarriers per resource block. Both systems use the same duration for frame, subframe, and slots. These timings are 10 milliseconds, 1 millisecond, and 500 microseconds respectively. Finally, the last major similarity is that both systems have 20 slots per frame. The following are differences between NB-IoT LTE and traditional LTE. NB-IoT uses a fixed system bandwidth. The system may only use one resource block that spans over 180 kilohertz. NB-IoT also utilizes its own custom PSS and SSS, called MPSS and NSSS, respectively. NSSS are sent in even frames, while MPSS are sent in both even and odd frames. The structure of these syncs also differ from traditional LTE. Instead of being spread across 6 resource blocks, these signals are grouped together in large blocks at subframes 5 and 9. Another difference between the two standards is that NB-IoT has 3 operational modes: in-band, guard-band, and standalone. This allows many options for IoT device creators who choose what frequency their device will communicate on. The MPSS is similar to conventional LTE. It is used to synchronize the UE and the time domain, as well as estimate the central frequency of the channel bandwidth. The main difference between LTE and NB-IoT primary sync signals are the number of subcarriers actually used to transport the signal. Traditional LTE uses 72 subcarriers, and they each send one symbol. Since these 72 subcarriers equates to 6 resource blocks, it's clear that NB-IoT, which is limited to one resource block, is unable to use the same format. NB-IoT changes the signal shape to be sent over 11 subcarriers, and they each send 11 symbols. The MPSS can be seen on the right. The role of the NSSS and NB-IoT LTE is to provide the in-cell ID and at least 3 significant bits of the system frame number. Finding these values allow for further communication between the ENB and the UE. The 3 main differences between traditional LTE and NB-IoT LTE is the derivation, distribution, and signal spacing of the secondary sync signal. The method of creation for the signal in LTE is an M sequence, while the NB-IoT signal is created with a 131 length Zadoff-Chu sequence. Traditional LTE distributes the SSS over 72 subcarriers, each one of these sending one symbol, while NB-IoT is again limited by the number of resource blocks it can have. This causes it to distribute the signal over 12 subcarriers, each sending 11 symbols. Finally, the NB-IoT NSSS is only sent over even frames.
NB-IoT LTE doesn't use the standard cell-specific reference signal, or CRS, that is found in conventional LTE. Instead, it uses a slightly modified version, the Narrowband Reference Signal, or NRS. The NRS acts as a reference point for downlink power, and it is also used to estimate the downlink channel. The NRS is sent in all subframes used for broadcast or downlink transmission, whether or not data is actually sent during that subframe. The NRS can be sent on either 1 or 2 antenna ports, and the resource element mapping for both cases is shown in the figure here. The Narrowband Physical Broadcast Channel, or NPBCH, is used exclusively to carry the Narrowband Master Information Block, or MIB-NB. This is a 34-bit long block that is transmitted over 64 radio frames, which takes approximately 640 milliseconds. The MIB-NB contains key information, including the system and hyperframe numbers, the System Information Block 1, or SIB1-NB, scheduling and size, the value tag, the access class barring status, and the operation mode. There is also some reserved space for future use. NPBCH uses QPSK, and the channel coding process is very similar to what is used in conventional LTE. The Narrowband Physical Downlink Shared Channel, or NPD-SCH, is used to send all downlink data for a UE. This channel carries all upper layer data in addition to paging messages, system information, and random access response messages. Because of the strict power consumption requirements of NB-IoT, the NPD-SCH uses tail-biting convolution codes, or TBCC, to reduce the system requirements. This is also why the maximum modulation level is restricted to QPSK. These limitations, however, mean the maximum transport block size is only 680 bits, which is significantly less than the 70,000 bits supported in traditional LTE. Lastly, the NPD-SCH is controlled using the Narrowband Physical Downlink Control Channel, which is described next. The Narrowband Physical Downlink Control Channel, or NPD-CCH, is the physical channel that carries the downlink control information, or DCI. The DCI contains information about which UEs have data and where to find it. In the NB-IoT LTE standard, there are only 3 types of DCI formats: N0, N1, and N2. N0 is used for the UL grant or NPU-SCH scheduling. N1 is used for DL scheduling or NPD-SCH scheduling, and N2 is used for paging and direct indication. In each subframe, there are 2 possible narrowband control channel elements, or NCCE0 and NCCE1. The NPD-CCH has 2 formats to choose from when using them. These are shown in the figure here. Format 0 uses 1 NCCE, which means that 2 can be sent within a single subframe. This is shown with the blue arrows. Format 1, however, uses 2 NCCEs, which is represented with the red arrow spanning all the subcarriers in the resource block. Next, we will go over the results from the project. Here is the experimental setup we used for this project. A picture of the actual setup is shown on the left-hand side, and a diagram of that same setup is shown on the right. We used a single computer with both an Atom Pluto and RTL SDR attached. In the photo, you can see both MATLAB and SDR Sharp running on the computer. In the following sections, we will go over how we handled waveform generation, visualization, transmission, and reception.
The MATLAB LTE toolbox was utilized to create the MB-IoT waveform in this project. Using the MB-IoT downlink waveform generator, we were able to feed in the desired parameters to custom create the signal. The bandwidth was set to be 1 resource block wide, as stated in the R14 specification. This equated to 12 subcarriers, each spaced 15 kHz apart. A total of 2 frames were sent to be able to show the difference between even and odd frames for the NSSS. The operations mode was set to standalone because of using an out-of-band frequency, and a carrier type of anchor was chosen as to include the MPSS and NSSS and MPBCH in the signal.
After the signal was defined based on the configured parameters, we use the built-in MATLAB function generateWaveform to create the signal. This function also returned the resource grid and a structure containing information about the OFDM waveform. The display resource grid method and the NB-IoT downlink waveform generator object was then used to create the resource grid of the generated waveform for all subframes, as shown in this figure. We then use the spectrum analyzer function from the digital signal processing toolbox to visualize the frequency response of the time domain signal, as shown here. This figure shows that the signal has approximately 180 kHz of bandwidth, which is expected since there are 12 subcarriers with 15 kHz spacing each. Outside of the 90 kHz offset in either direction, the power of the signal decreases significantly. However, there is still some power at these side lobes, which can cause interference when transmitting and receiving NB-IoT signals. This next figure shows the time domain representation of the generated waveform. This is the signal that is actually created and transmitted using the Atom Pluto. Here we see a side-by-side comparison of the experimental on the left and theoretical on the right resource grids for NB-IoT LTE. The format of these resource grids varies, like the colors, axes, and scaling. However, taking these differences into account, the resource grid for the experimental waveform matches the expected resource grid for the NB-IoT standard.
The waveform transmission was achieved using the DOM Pluto SDR and its MATLAB support package. MATLAB provides an input-output abstraction for the MATLAB Pluto communications. To achieve the setup, a Pluto system object had to be created in MATLAB. The center frequency of 850.5 MHz and sampling frequency of 1.92 megasamples per second were specified. The center frequency was chosen due to low activity in the spectrum. Since the Pluto does not have extremely high transmit power, interference with other signals was not a major worry. The final step in sending data was to pass the complex waveform into the system object. The device then initializes and sends the data at the specified frequency.
Waveform reception was primarily done using the SDR Sharp platform. The sample rate of the controller was set to 1.92 megasamples per second to be consistent with the sample rate used for waveform generation and transmission. This figure shows what was displayed on SDR Sharp prior to receiving the signal. This provides a baseline that can be used for comparison later. This next figure shows SDR Sharp during the reception of the waveform. Power is centered around the 850.5 MHz frequency, but the signal is picked up in the surrounding frequencies as well. This last screenshot was taken after the transmission and reception were complete. As you can see, the channel is quiet once again. The bottom plot in this figure shows the magnitude of the received signal over time across all frequencies. We can see the received waveform in red. The next logical step in this project would be to decode the received waveform. However, there were a number of factors limiting the project. The hardware available was the biggest obstacle in this project. We only had one Atom Pluto available to use, which meant we had to use an RTL SDR for reception. This led to an issue of insufficient sampling frequency. The maximum sample rate for the RTL SDR in SDR sharp is 3.2 megasamples per second, but the Nyquist sampling rate would require 140 megasamples per second. Without a large enough sampling frequency, filtering and demodulation of the received NB IoT signal was not possible.
The next steps in the project would be to obtain another Pluto SDR. This would allow us to more easily transmit and receive signals. The Pluto is much more powerful than the RTL SDR, so it would help us sample at higher rates than previously done. Next, NB-IoT search functions should be implemented in MATLAB. The LTE toolbox has built-in self-search and frequency offset functions. These are not suitable for the NB-IoT application because they adhere to the traditional LTE standards. The major feature being that the functions only accept a minimum of 6 resource blocks due to the differences in control signals. GNU Radio is another direction the work could be taken. GNU Radio is a free software development toolkit that provides signal processing blocks to implement software-defined radios and signal processing systems. This would allow block diagrams to be created to easily create the systems needed for NB-IoT communication. After getting the transmit and receive system set up, experiments using real data may be performed. This could be pictures or other types of data. Finally, obtaining real IoT devices that use NB-IoT and testing them with the receiver setup would test this work in a real operational system.